Okay, YouTube, this is my third video on solving equations, in which we're going to confront how you work with equations that involve, pretty heavy fractional expressions. And so let's go ahead and start by considering this equation right here. I say solve the following linear equation by eliminating the denominator first, and then check your solutions when you're done solving it. The idea is that what we're going to do when we deal with fractions or expressions that have fractions in equations is we could just eliminate the denominator. It's a lot easier to work with things that do not have fractions. Okay, so the way we do this is essentially this. We say if an equation does involve fractions, then we can rewrite the equation into a form that excludes any fractions by first multiplying both sides of the equation by the LCD. So the key step here is this. Before we do anything, we're going to multiply both sides by the least common denominator. And the thing is, to find the least common denominator, recall the easy way to do this is if I were to say factor all of the denominators here, I would have an expression that say x minus 3 over 2 times 2. This is equal to 5 over 2 times 7. And we say minus x plus 5, that is over just 7. The idea is when you want to get an LCD, the easy way to do it is you say, okay, well, list the factors that you have in the first denominator there. So I have a 2 and a 2, and then list any from the other denominators that aren't currently in its list. So like I already have a 2 there. I can see 2 2's, but I don't have any of these 7's yet. So I would like build in a 7. So 2 times 2 times 7 is 28. The idea is that the least common denominator between all of these then is 28. So the way we're going to solve this equation is just this way. We're going to take this, both sides of this equation, we're going to multiply by the same value here. So I would get a new expression that looks like this. We say 28 now times 5/14 minus x plus 5 over 7. And so we're going to simplify both sides of this. The way this is going to work, though, is because if this is 28 over 1 times this over 4, then you multiply straight across, but we can cross-reduce here. I could say, well, I know that 4 is a factor of 28 by the fact that, the LCD is by definition containing all of these factors here of the original expressions in the denominators. So we'd say this would become a 7. And if I take 7 now, we say 7 times all of the numerator, 7 times x minus 3, we get that. Now on the right side, we're going to have to do this twice, but I'm going to say that this 14 and this 28 cross-reduce. This 14 would become 1, and the 28 would become a 2. So now if I were to take, say 2 times that 5 right there, we would get this. We would get 10. And I'd say now take the 28 times over here, and we say, well, this 7 and the 28 cross-reduce. The 7 has to become a 1, but the 28 this time becomes a 4. And if you send a 4 through, remember, you got to take that 4 times all of this expression right here. So I'm going to bring down the negative here, this minus. We say minus 4 times all of the quantity x plus 5. So now solving this equation, we'll do that. We'll say, we'll just go ahead and simplify both sides. We get 7x minus 21 constants. Here we get 10, and now I've got to distribute a negative 4 through. We could also look at that as, plus a negative 4. So we would say, okay, well, negative 4 times x is negative 4x. And we say negative 4 times this positive 5 is negative 20. So now our idea would be this. We're going to combine like terms and get all of our x's on one side of this equation. So if I said, well, I've got a negative 4x over here, a positive 10 and a negative 20 gives us a negative 10, I'm going to add 4x to both sides. I want to get all of my x's on one side now. We'd say, well, then this side they would cancel, and I get 11x here minus 21 is equal to negative 10. And if I were to now add 21 to both sides, add 21, notice what we get. It's a nice, pretty number here, but we get 11x is equal to 11, and dividing by 11 gives us a new equivalent equation here. So we would say that it turns out that it follows that x is equal to 1, and we also want to write this in set notation. So we say the set of solutions for x is this guy right here. So now what I want to do is check my solution. And one way to do that is to plug it back in. Another way to do it is to check it on our calculator. So in our last example, as a matter of fact, I'm going to change my window here. I'm going to go and basically put this expression in for y1, and I'm going to put this expression in for y2, and we're going to go look at the graphs of these. And I'm going to say, where does y1 equal y2? Or in other words, where do their graphs intersect at what x value? And I'm telling you, I bet they do at 1. So when I put this in, and I have this old graphing window here, first thing I'm going to do is I'm going to hit zoom 6. I'm going to go back to my standard window here. But I've already typed these expressions in. Now, one thing I do want to comment on is this. This x minus 3 over 4, you have to put the x minus 3 as a quantity that is in parentheses. And so I put that in as y1. Now, the right side of this equation, even worse with parentheses, 5/14 has to have its own set of parentheses. And then we're subtracting all of this, of which we have to put x plus 5 in parentheses. So we have parenthesis, x plus 5 end parenthesis divided by 7 and then end parenthesis. But I'm going to go ahead and turn these graphs back on. Enter. I'll go over my equal signs. And I'll hit enter here. And we're assuming that when x equals 1, we have a common graph point. And so it's kind of hard to see here. I'll go to zoom and go to zoom in. you get this little blip here. Right now it says it's at 0, 0. I'll kind of zoom to the right where x is kind of 1 and down a little bit. It looks like they hit there. If I hit enter again, you can see that we get kind of a zoomed in picture. And it says when x is equal to 1, we have a common y value. So to find this, we'll go back to our intersect function here, which is second trace and then 5. It's going to say, okay, so what's your first curve? And just to show you here that we have, this cursor actually moves. I'm going to go to the left a little bit here. It says, what's your first curve? I say, well, that's my first curve. This is my second curve. So I've highlighted the two curves. And then it says, guess where you think this point of intersection is? So I'll kind of come to the right. It doesn't have to be perfect, and I'll hit enter. And it says that you have a common intersection point of -1/2 when x is equal to 1. So the point here is that they intersect when x is equal to 1. And that's what we want down here. And before I leave off, I also want to go to our table. And we say, if I go to a table of values, we say when x is equal to 1, I'll scroll back here. You can say when x is equal to 1, notice that they both have an output value of -1/2. Or in other words, both sides of this equation will be equal if x is equal to 1. We can see that here. Cheers.